16.1 Inclined planes. The inclined plane problem is a classic problem in an introductory physics course. Nearly everyone who takes introductory physics has to solve an inclined plane problem. The setup looks like this. You have an incline, which is at an angle, and an object is placed on this surface. The object usually is given a mass, and we know that gravity always points directly down. The reason why these problems are challenging is because the normal force comes out perpendicular to the incline, so it's not pointing the same way as gravity, and sometimes we even add friction and a coefficient of friction into the problem as well. Because force of gravity is not equal to normal force, we have a more challenging problem. We know that they're not equal because they are pointing at angles to each other, which means that they can't directly cancel each other out or equalize each other. These problems are much simpler when you consider that you can take your normal xy plane and rotate it. So the x-axis becomes parallel to the incline of the plane, and the y-axis becomes perpendicular to it. When you do this, now it's only gravity that's at an angle, and everything else falls into our coordinate system. Gravity can be then broken down into an x component and a y component, or a component that is parallel to the incline and a component that is perpendicular. When you draw this triangle, the angle of the incline goes on the top of the triangle. This is always going to be important, and so make sure you memorize this. Put the angle at the top of the gravity triangle. And you can go through the complicated geometry to figure out why this is true, or you can just take my word for it. It goes at the top of the gravity triangle. We're going to go through 5 steps that can be used to find the acceleration in an inclined plane problem. Most commonly in these problems, you'll be asked to find the acceleration, and usually you'll be given friction as well. So here are the 5 steps. Step 1, find the components of gravity. Remember, we've created a triangle out of gravity. Now gravity has an x component and a y component, the x component parallel to the incline and the y component perpendicular. When you go to draw in your components, make sure you put the x component parallel, the y component perpendicular, and don't forget to put the angle of the incline at the top of the gravity triangle. Looking at this triangle on a larger scale, we're able to break down the components into their equations using trigonometry. We'll start by writing out Fg is equal to mass times the acceleration due to gravity, which is small g. Y is adjacent to theta, so we'll use cos, and x is opposite to theta, so we'll use sine. This is different than normal. Traditionally, y uses sine, but this triangle is different than normal, so you need to be ready to throw in your different trig equations. Fg at y is Fg cos theta. Fgx is Fg sine theta, which is mg cos theta and mg sine theta. We'll save these formulas for later because we're going to need them. The second step is to use Fgy to find the normal force. If we consider our incline again, we can see how this can be done. Fgy is running perpendicular to the incline down, and Fn is pointing directly opposite to it. Now we've found a force that perfectly balances out Fn, so Fn equals Fgy. This is mg cos theta. Step 3 is to find the force of friction. We know from our study of friction in the last video that the force of friction is equal to the coefficient of friction times the normal force. This means the force of friction is mu mg cos theta. Again, we'll save this formula because we're going to need it again in a little bit. The fourth step is to find the net force down the incline. We know that the object isn't sliding through the incline because the normal force and Fgy cancel each other out. That leaves us with the x forces, Fgx, and the force of friction which opposes it. The net force on the incline is Fgx minus the force of friction. Combining all the formulas we have so far, Fnet is mg sine theta minus force of friction, which is mu mg cos theta. This brings us to our final step. Step 5 is use the Fnet to find the acceleration. This comes from Newton's second law. The acceleration is equal to the net force divided by the mass of the object. So the acceleration is mg sine theta minus mu mg cos theta divided by m. And using our knowledge of algebra, we see that there's two masses in the terms on the top and a mass on the bottom, so mass can cancel out. This gives us an acceleration equal to g sine theta minus mu g cos theta. The steps we've just taken here is a process called deriving a new formula. This is something that we do in physics a lot, and it's in fact a fundamental skill for later on in Physics 30. You'll need to be able to take multi-step problems, combine the formulas to create a brand new formula. When you derive formulas, you use algebra to combine a collection of other formulas that are related to each other and related to the problem into a new formula. This sometimes can make things much simpler because you only need to take one step to solve for something instead of solving and finding bigger and bigger numbers with lots of decimal places. I'll show you this in the next example. Here's an incline, which is 15-degree angle, and we're going to place a 3.2 kilogram object on it. The coefficient of friction between the object and the surface is 0.25. We know the force of gravity pulls the object down, and this gravity can be broken down into Fgy and Fgx. The normal force opposes Fgy, and the force of friction opposes Fgx. Here's the quick method for calculating the acceleration. Acceleration equals g sine theta minus mu g cos theta. This is the formula we derived in our 5 steps before. This is 9.81 sine 15 minus 0.25 times 9.81 cos 15. And all in one step, we find acceleration equals 0.17 meters per second squared down the incline. Now, I wouldn't be much of a physics teacher if I stopped there. I do need to show you the 5-step longer method because sometimes you're going to need to show me all the steps. The first step is to find Fgx. Fgx is Fg sine theta, which is mg sine theta, which is 3.2 times 9.81 times sine 15, which is 8.1248 newtons. Fgy is Fg cos theta, which is mg cos theta, 3.2 times 9.81 times cos 15. This gives us 30.2 32234 newtons. All this was the first step. Step 2 is to find the normal force using FGY. The normal force is FGY is 30.32234 newtons. And step 3 uses this normal force to find the force of friction. Force of friction is mu Fn is 0.25 times 30.32234 newtons, which gives us a force of friction equal to 7.580586 newtons. Step 4 is to find F net using Fgx and the force of friction. This is 8.1248 minus 7.580586 newtons, which gives us a net force of 0.54421 newtons. Step 5, the final step, is to use this F net to find the acceleration. Acceleration equals F net divided by mass, which is 0.4421 newtons divided by 3.2 kilograms, or 0.17 meters per second squared down the incline. And you can see, using all 5 steps where you show all the pieces, and using the quick method, the derived formula, we'll always get the same acceleration.